Okay, so let's see now the backpropagation again, but now from a different perspective. So let us take our network that we had before. We have a couple of layers. The first layer had 50 hidden neurons. So the input will be these 784, and the output will be 50. And then we have the bias, and then it is producing these vectors, and then we have this A1, that is the sigma activation, so the non-linear function applied on the linear part. And then we have the second layer. The second layer had 10 neurons as output. The input will be 50, because it is the input from the previous layer, and then times 10 just to produce the 10 components that we need for the last one, plus V2. You have to remind that this plus V2, this weight, the bias will be integrated into the matrix with a column of ones, so with an input of ones, and then we have the output of the second layer. So we have, this is what we predict, this is the ground truth, and then the cause function will be this cross entropy that we have here. Okay, so now we can try to explain the backpropagation from a different perspective. So we will have a couple of vectors. We will have to keep track of these couple of vectors. One will be called errors, that are the derivative of the partial derivative of the cause function with respect to the activation. And so here we have with respect to activation in the second layer, with respect to the activation in the first layer. The other one will be called deltas, that are the derivative of the cause function with respect to the linear part of those layers. And the same here. But we can also look at the structure of these derivatives. So C with respect to A2, okay, that's clear. But then we have delta, that is C with respect to Z2. But with respect to Z2 is the partial derivative of C with respect to A2, and then the partial derivative of A2 with respect to Z2. And the same here. So we have E1. E1 is C with respect to A1. But C with respect to A1 is C with respect to A2, A2 with respect to Z2, Z2 with respect to A1. And the same here, C with respect to Z1 will be C to A2, A2 to Z2, Z2 to A1, and A1 to Z1. Actually, there is a nested structure. So this one, E2, is what we have in here. So this vector is just this one, and then it is the multiplication of something we have already computed times some other vector. And then this one, we have two components, or the multiplication of two things that we have already here. So this is delta. So this is delta times something else. And these three are these three here. So these three is just E1 with respect to this one. So this is E2, this is E1. So deltas are the previous E's, so the E2, E1, so the E from the current layer times this derivative. And then at some point we have to compute the derivative of C with respect to the weights. But the C with respect to the weights will be C with respect to Z1, that is, or Zi, that are these delta vectors that we have defined, times the delta Z with respect to the weight matrix. But this weight matrix, because of this, it is just delta times this one. Okay, so this is for the weights as we have seen it. Okay, so I have taken this code from this web page. So this web page explains the backpropagation in terms of code, and it is again an implementation of a very simple layer or neural network from scratch. And then this other link goes to a web page where they describe the backpropagation in a more mathematical way. Okay, so let's make some comments on this code. The first thing is that we start in a reverse way. So we start propagating the error from the end of the network towards the beginning. Then we have, so for the last layer, we go through this else. So we have to compute the derivative of E2, so the derivative of C, the coast function with respect to A2. Here, in this, for the loss function they have chosen in this example, this derivative is simply the difference between the output of the layer and so the output of the layer and the expected value. So this is the ground truth. Okay, so okay, so far so good. Then we finish this with the last layer. We go so we have to finish that. So we have to compute the delta for the last layer. So the delta for the last layer will be, so we take we point to the layer. So this is this neuron. So we point to the layer, and then the delta will be this. So delta is this vector times this one. So it is this vector that we have called errors, and so we have called it errors. So it is errors times the derivative of A with respect to the output, to the set. So this is set is the neuron output. So this is set, and then we are computing the derivative of A with respect to set. So this term is this one, this term is this one, and we are computing neuron delta, that is the delta that is the derivative of the coast with respect to set 2. Okay, so then we are done with the last layer. We go for the next layer. So for the next layer, we no longer go this way, but we go this way. And then what we have is this E. So we have to compute E. E here, it is the W2 transpose times delta 2. So times delta 2, and this weight is this one. So actually this W2 comes from the derivative of set with respect to the previous activation. So the previous activation, so for this matrix, so for this set 2, the derivative of set 2 with respect to this one is just this matrix, W2 transpose. And then we have to multiply by delta 2. But delta 2, that is this part, we have stored in this structure called neuron delta. And here you see something that also happens when you use these libraries, PyTorch, TensorFlow, and so on. That is, it is not only that you need a space or you need memory to keep all the activations and sets and so on of the different layers, but you also need to keep track of the errors, so these E vectors and the delta vectors. So you will need a lot of space. And as we saw in the previous implementation, in the previous lecture, you also, if you are using some optimizer that needs momentum or that needs any other vector, then you will also need the vectors for all those momentum and the speeds and whatever. So it is not only the forward propagation that is relatively straightforward, but also you will need a lot of memory to do the back propagation. Then you update again. So this update, these errors is this vector here, you have it also there, and then the derivative of delta A, so the derivative of A with respect to Z. So it is this derivative of the transfer function, this activation function, the nonlinear part, evaluated at the output, evaluated at A1. And so that's it. And then you have to update the weights. So you have now computed through this code, you have computed all the delta and the E vectors, so the deltas and the error vectors, and now you have to update the weights. So the weight is you follow a gradient descent, for instance. So the gradient descent, it is the derivative of C with respect to W, but C with respect to W, we saw it here, C with respect to W, it is the delta times the activation of the previous layer. So that is what we should see in the code. So it is the delta times the input of the previous layer, and or the input to that layer. So coming. So there is this correction here. So this correction is because the B, so the bias, the input is always 1. So the input should be 1. So we update it in this way. And this is it for this second view of the gradient descent. Yeah, and the backpropagation.